Welcome to this lecture series in number theory. Last time we defined the Euler's torsion function, which let me recall. So the torsion function was defined as a function from naturals to naturals. So when you feed it the value n, what it outputs is the number of positive integers in this range which are relatively prime to n. So that was the definition. And we saw this key multiplicative property of it, which is that if you have two relatively prime positive integers, then phi of the product is product of their phi's. Okay, and a consequence of this is that you can calculate it. You can calculate the value of phi at any input given or known once you know the prime factorization of that number. So if n is written in this fashion where p1 up to pr are distinct primes, then phi of n is this number where for any prime p we saw that phi of p to the power k is given by this expression. Alright, so let's move on. Some problems for practice. And now let us get started. So today we'll have a very short lecture. What we want to discuss is Euler's generalization of Fermat's little theorem. And we will have a short discussion. Generally, I would like to take some concrete examples and illustrate the mechanism of the theorem before proving the actual theorem, but since we have already done Fermat's little theorem in some detail, the discussion here is very similar, so I won't take too much time. So what does the theorem say? Suppose you have any positive integer n. Then we claim that this congruence holds whenever a is relatively prime with n. So you pick any a that is relatively prime with n, then this congruence holds, right? And you can immediately see that this generalizes Fermat's little theorem, because if n is a prime, then phi of p is what? Suppose n is equal to p, a prime, then phi of n is p minus 1, and therefore you immediately see that that becomes Fermat's little theorem. Okay, and the proof is nothing different from what we did in the case of Fermat's. So here is the details. Yeah, so let S be the set of all those positive integers which are in this range and which are relatively prime to n. Okay, clearly the size of S is phi n, that's how phi was defined. And now define this function, call it f from S to S as f of x is ax, but here there's a little catch. I'd like to say, let me change the set S, let me write it this way, and by the discussion in the previous lecture, by a little comment that we made, everything is still absolutely fine. This mod S is still phi of n and so on. So let me write f of x as ax mod n. As usual, what this means is this thing on the right hand side is what? Is the remainder of ax when you divide it by n. A times x is some number. You get the remainder of it when you divide it by n. The remainder will lie in this range. So, well, so far we know that f of x is in this range, but why should we believe that it also satisfies this condition? Why? Because we are asking, we said that we are defining a function from S to S, but we haven't justified that f of x lies in S, but it's very simple. The reason is a is relatively prime to n, x is relatively prime to n, so their product will also be relatively prime to n, and therefore we already have this. So we have justified it. Right, so f is a function from S to S, just think about it if it is not clear. And in fact, f is an injection. F is an injection because if fx equals fy, then ax would be congruent to ay mod n. And now, as usual, you can do it in two ways. Either you use the fact that a is invertible modulo n, so you multiply both sides with the inverse of a and you will get rid of a, and you will obtain that x is congruent to y mod n. Or you can do this thing you write the above congruence as follows. This thing happens, mod n, and therefore n divides this guy, but a is relatively prime with n, so you can drop it, and therefore n divides x minus y. So at any rate, what we will get is that x is congruent to y mod n, because a is relatively prime to n. Okay, and then it means that x is equal to y. Because x and y are in this range, it would automatically mean that x is equal to y. So therefore f is an injection. We have done this kind of reasoning many times, and hence f is a bijection. Right, it is an injection, but it is from the same finite set to itself, and hence a bijection. And therefore the product of all the things in S is same as the product of their images under F. Simply because as you vary over S, all you are getting are elements of S just in some permuted order. So this is a pointwise, this is not just modulo n true, this is true as numbers. This natural number is equal to that natural number, and hence this is also true modulo n. But before I write that, let me do one more step. This product is equal to a to the power. Yeah, so let me first write modulo n, that would be better. This is congruent to that thing modulo n. But now we can write this is congruent to product a times x modulo n. And that gives us that this product is congruent to a to the power phi n times the same product. Now what happened here? How many times is this product appearing? Mod s times, but mod s is phi n. So basically a is getting multiplied by itself phi n times, and therefore we see this term over here, and everything else is here. And now the same thing, this is relatively prime to n, because every x that we see over here is relatively prime to n. Right? This is the clubbing property or whatever. This is something that we already used somewhere here. I think we used here. Anyway, so therefore you get the thing that we wanted. This gives us that 1 is congruent to a to the phi n mod n. As usual, you can either multiply by the inverse of this number on both sides, or you can do the subtraction thingy and etc. etc. So that proves Euler's theorem. And yeah, let's see an application, and that will be it. So we are asked to find out what are the last 2 digits of this number. Right, so it's not very directly doable. For example, the way you would do it, the most natural way perhaps would be to, find the order of 3 modulo 100. So before we even say that, observe that finding the last 2 digits of any number is basically asking us to find the remainder of that number modulo 100. So we just want to find the remainder modulo 100. So you can obtain the order of 3 modulo 100, and then you can proceed. Fermat's little theorem, Euler's generalization just cuts short some of these steps. So here is how we can do it. This is a solution to the problem. We know that 3 to the power phi of 100 is congruent to 1 mod 100, because 3 is relatively prime with 100. And what is phi of 100? Phi of 100 is 100 times the primes. Well, it depends only on the primes now that divide 100. 100 times this product, because 2 and 5 are the only primes that divide 100. We have phi of 100 is this thing, which is equal to this number, which is I think 40. Yeah, so we see that 3 to the power 40 is congruent to 1 mod 100. And now we will find the remainder of this guy modulo 40 and so on and so on. So let's multiply both sides by or raise both sides to the power 4. So we will, not 4, maybe power 6. So raising both sides to the power 6, we get this congruence, which gives us that 3 to the power 240 into 3 to the power 16 is congruent to 1 mod, not 1, but congruent to 3 to the power 16 mod 100. So on the left, we have 3 to the power 256. That is what we were trying to worry about. And on the right, we have 3 to the power 16. And now one can do it any which way. So let's see. 3 to the power 5 is what? 243. So let me write the right hand side as 3 to the power 5 into 3 to the power 5 into 3 to the power 5 into 3. But 3 to the power 5 is 243, which is something I'll write as 43. So it is 43 cube into 3. But now it's some computation. So 43 square is something. So 43 square is congruent to 49 modulo 100. So we get, this is congruent to, let me write one more step. So that's 49, and 43 into 3 is what? 3 3 is 9. Yeah, but I can remove that one because we are only interested in modulo 100. So that's the thing. And now one more computation, 49 into 29. So it's 21. So the last two digits of this number are 2 and 1. Okay, so yeah, with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.